you again, everyone, for joining the webinar. As you can see, or as you know from the several emails that you've received and LinkedIn posts, today's webinar is about test as you fly, fly as you test, how to stay agile and compliant in a SpaceX-Rideshare world. What we'll do today, we'll clear up what test as you fly and fly as you test really means, and how to stay compliant without slowing down engineering velocity, and how we tease also the Dcubed resettable mechanisms enable both. You won't hear, lucky for you, only about me today. I am here with some of my colleagues and two of our customers. So thank you also, Kyle and Guillaume, for being on our side. On my side, who am I? So Valentina Lucchetti, I work at Dcubed as a senior sales manager, mainly focusing on the European and APAC. Kyle is my colleague also on the sales side, focusing more on the Americas and the Middle East, while Guillaume Quintana Will is the lead customer solutions engineer. On the customer side, again, thank you for joining us today. Benjamin Rodigar, who's project manager at DLR, and Dave Powie, who's senior spacecraft mechanical engineer at Hubble. To get started, actually, before going into the topic, we'd like to hear more from you. Hold on just 1 second. So, regarding the agenda, we'll go through a quick introduction, but before that, we'll hear about, from you on what is sort of your understanding right now of the test as you fly, fly as you test, and what you think are sort of the biggest challenges that you have. We'll then say on our side how to solve, or how we think that this new rule from SpaceX can be well made. We can comply with that in a very easy way, and with that, the most common misconception of the rule. Then, thanks to Guillaume, we'll go through a short demo of the Dcubed's latest resettable release actuators. With Kyle, we'll do a fireside chat with Ben and Dave. So to hear real-world test as you fly, fly as you test engineering experience. Guillaume again then will share technical lessons learned on regarding integration and verification of some of our actuators that apply to the Dcubed actuators, but in general, of course, to resettable ones. And we'll wrap up with questions. Very important point, as you may have read in the emails that you received, there's a small giveaway for the best questions that will be asked throughout the webinar. So make sure to submit them at any point during the webinar in the Q&A tab that you should have access to. And at the end of the webinar, we'll go through a Q&A, and after that, we'll announce the winner. And the goodie this year is a Dcubed hat. So almost ready for the sunny days. So to hear from you now, before starting on my side, I'd like to ask everyone to take your phone, scan, or through Slido, scan the QR code, and let us know what is your biggest test as you fly, fly as you test compliance challenge. I'll pause here and wait for results to come in. First answer is coming in. So far, retest re-verification delays after hardware changes is the biggest challenge? Keeps winning. I'll wait another 1-2 minutes. Oh wow, it's hitting 75%. Okay. Anyone else voting in that we should be waiting for? 20 people so far voted. All right, I'd say we are pretty set. Oh, someone just voted an additional one for the same. And most probably, well, I will eventually leave PM later to comment more, but as I'm also an engineer, I would also most probably struggle the most with the retest and the re-verification of delay in case an hardware needs to be like changed or and then retested and everything. But let's now do something more. So let's see how we can play the test as you fly and fly as you test as an enabler of agile spacecraft development. Because sure, the rule is there, and SpaceX is imposing that on everyone. But I would say that right now in the world there are actually things that allow it to be smooth and actually played on everyone's paper. If we start with time, for example, I guess it's every engineer's dream to test as fast as we iterate. So instead of waiting every time, okay, we've done an iteration of the of a component, let's order again the new HERM to test it again because we've used a barn wire, for example, or a pyro, and we need a new one. So what test as you fly and fly as you test says is not that, like, it's that no unverified changes are not allowed, but not that changes are not allowed. So we can always change the design. What is important on, let's say, the party that is building the hardware is just to be fast on then applying those changes. So the development agility is preserved if the re-verification is fast and controlled. And what you can do is, for example, that thanks to SMA resettable mechanisms, so shape memory resettable mechanisms, you eliminate weeks of retest planning because you enable component test, flight test cycles on the actual flight hardware. So in this case, for example, the bottleneck is not really the rule, it's more the hardware choice that in the end, during the project, you make. If we check on the cost side of things instead, how can we reduce? Because as engineers, we sort of carry less of the cost of the project, but then the project managers comes to our shoulders. It's like, hey guys, we're going over budget. Let's please check what we're doing, decisions of components we're taking, how much time we're spending on an hardware. So if at the beginning of the project, particularly maybe from a project management side, it looks like barn wire, pyros, or fuse wires are cheaper because the cost, of course, of one fuse wire compared to a shape memory alloy is for sure cheaper. There's no big tech, let's say, behind a barn wire. As soon as the engineering teams need to do test and retest, the costs start summing up, right? And you also need to spend a lot of time on the disassembly and time also of the engineering of cost. Every time that you order a new part, you need to go through a lot of new paperwork for procurement, but also incoming inspection and all of that. And at the end of the day, you need also to spend time and cost on a requalification. So what you can do instead, again, with an SMA upgrader, but also what we do at Dcubed, is that instead of every time giving you, or instead of like needing to order a new actuators every time, what we do is even offer on top of a fully resettable actuators free consultancy hours. And that's where the title, for example, of DM directly comes in as customer solutions engineer. It's like if we always sell a piece of DM with our product, and whenever you have a question, can be the most stupid one, or you maybe get into trouble during a qualification campaign, you call DM, you call his team, and they're going to be there ready to support you. Last but not least, on the complexity, in the end, the more you like, the way to reduce risk is to reduce the complexity of the design. What Test As You Fly, Fly As You Test is is fundamentally about configuration parity. So resettable HVRMs maintain this parity through multiple test cycles, meaning that, as long as the configuration is the same, and so you don't have struggles. And a fast restore, for example, and rearm prevents also divergence between test and flight configurations. So at the end of the day, the easiest way to stay compliant is to avoid anything that could break the configuration of your hardware. Done with sort of the lesson. What I believe now we should see is some of our, for example, the Dcubed actuators in action, and how this would enable you to really with the project. So Ian, I'm calling you on this virtual stage. Can you please introduce to us the latest products of Dcubed that were developed and put in the market, and then also show us how easily they can be triggered and reset?
Yeah, definitely. So I have with me, I'm not sure if you can stop sharing the screen so that they can see my video, but I have with me over there.
Outlining for everyone. Can everyone see Ian? It work? Oh wait, I've spotlight the wrong DM. Or DM's
Yes, can you see
there
it?
again? Yeah, but we don't see the hardware. Yes.
Now you can see my screen, or?
We can see the hardware.
All right, all right. So basically, we have over here some actuators. The newest ones that we have qualified recently at the beginning of this year is the micropin puller, which is that device. I'm loving the color and the form factor of this micropin puller. The main differences is compared to the nanopin puller is that it's 10x in terms of force. You can load it radially, like side load, instead of like making some pulling force and so on. You load it side load, which is kind of convenient for optical payloads. Also, the aludyne itself, which is the coating that we have over here, it's a super low outgassing coating. It's outgassing way less than the normal anodization, and therefore for optical payloads or anything that has optical elements nearby, it's a really convenient one. Additionally, also the aludyne, it's super conductive. So in terms of grounding, this thing it's never going to be charged in terms of ESD and so on. It's a really cool device. The force that it has on the stroke, like pulling force, it's 80 newtons, and the maximum force that you can put on the side, it's 490 newtons while keeping the actuation. And for instance, a classical application for this kind of device will be gimbal kind of applications or anything that needs to rotate, like this setup. Basically, we have the pin puller over there from the bottom side. What we are recommending is to have this bushing over there, the golden one. Use it as a load interface, so a tight fitting, so any kind of side load it's going to be taken by this bushing. And then on the mating part, what is kind of important is that if you have different materials between the moving part or the playable part and the bottom one, you need to be aware of which is the actual degree of freedom that you want to lock. In that case, it will be rotation. So we have made a slot over there so that if there was any kind of thermal expansion, this thermal expansion is not going to add unnecessary loads into the actuator. And the way that it works, I'm going to just quickly trigger this unit. It requires 2 amps, and with those 2 amps, the trigger should be kind of super fast, less than 1 second in normal conditions. Of course, it depends on the temperature, and it depends as well on the side load. So there we go. Well, I hope you have heard the actuation of the device, and now this thing is free to spin, and that will be the purpose of the pin pullers. Then the second actuator that we have recently qualified, it's this other one. This is the milli-release nut. That one is working slightly differently, so instead of like getting inside, it's popping out. This is the kind of shiny part, that's the nut itself. It's not going to be shiny. Actually, this is just for demo purposes. But the real one is going to come in this color, this shape of color. This is a 17.4 pH with a process, a hardening process that is called plasma nitration. And what is unique about this device is the reset and the loading capability. There's no other device in the market with this loading capability that it's so easy to reset. And for that, I'm going to demonstrate how this device is working.
Yeah.
Something that is...
Can you remember to everyone what's the load of that?
Yeah, absolutely. So the maximum load that those devices can take is 15 kilonewtons, and it can take this load all the way up to 12 actuations. If the load is decreased, let's say 12 kilonewtons or 10 kilonewtons, this device can take more than 80 actuations. So as you can see, there's a lot of margin for customers to play around them and do some development stuff, verification and testing, and still fly the same unit that they have used for all those verifications and so on. So the unit itself, as you can see on the nut, it has some slots that are interfacing with the locking bolts, which means that you can directly apply load through torque, as I'm going to do right now. So I have this torque wrench set to 6 Newton meters. This is not going to provide the 15 kilonewtons, but since I'm using my hand to counter the torque, I'm not that really strong. I should go to the gym, so that's the best I can do.
That example, Guillaume, that you're setting right now.
Yeah, most people should go to the gym, me especially, but never mind. So yeah, something that is different from this actuator, as I was mentioning, is the way that it receives the power. This device is not meant to be used for, in terms of power, it's not meant to be used with a constant current supply. It's meant to be used with constant voltage. So right now, I'm going to increase the voltage to 24 volts. The device itself, it can take anything between 24 and 32 volts, so that customers, they can directly plug those actuators into the satellite bus, which it's fairly convenient. The only difference is that the higher the voltage, the faster the actuator is going to be. And in that regard, have in mind 24 volts, the trigger time, it's around 8 seconds more or less. So I'm going to power the unit. And what you will notice as well is that those units, they require a minimum preload. So over here, we have a stack of bell washers that was providing this stroke and the pulling out. And now let's go to the part that is unique about those devices. The device itself, it can be reset with one finger, with the thumb. The only thing is that because I have the bracket and my thumb is not going down that well, I'm going to use a spacer. So with this spacer, I just need to push it, and now it's ready to go. You can test it again, and we can preload it one more time. And that's what is beautiful about this device. You can get 15 kilonewtons and reset it in a matter of seconds. Normally, the recommendation is to wait a bit longer, just to make sure that the device can cool down a bit. But as you can see, it's already taking the load. And there we go. Now it's perfectly loaded again, after a few seconds. And we can fire once more the device. And And there we go. So this is it.
Thank you very much, DM. I will give, in case you have, guys, any questions about the actuators, or you want to ask DM something, feel free to drop again the questions in a chat, and later on we'll go through that. What we'll do now, moving from PMs and from the demo of these two actuators, we'll go to listen to direct life experience of our customers with our products. Kyle, I'll hand it over to you, and Ben and Dave.
Thanks, Valentina. So guys, I'm Kyle Megna. I'm our sales and business development manager for the Americas, here with Ben from DLR and Dave from Hubble Networks. One of the coolest parts of my job is getting to hear about the awesome projects that our customers are working on. So Ben and Dave, if you guys just want to take a turn just introducing yourselves, what your company does, and maybe the specific projects you've been working on, then we can dive into the questions here.
Perfect. I would start at a point. Kyle, thank you very much for the introduction. Thank you very much for having me. My name is Benjamin Rödiger. I'm working at German Aerospace Center for a bit more than 11 years now. I'm a project manager, and we are building laser communication terminals for CubeSats and for small satellites. And we had the challenge that we also have very high sensitive parts because of the optics, and still have to face the harsh environment during launch and during qualification. And that was when we then came to the solutions by Dcubed.
Hey, I'm David Powie. I'm a senior spacecraft mechanical engineer at Hubble Network. We are a growing company that is developing a global Bluetooth network for IoT devices, and that includes direct-to-satellite communication. We have 7 satellites in orbit right now that are all 16U CubeSats. And I was involved in the development of the payloads, both internal electronic payloads and deployable antennas on all those. And all those satellites so far have used the Dcubed nano release nut. So yeah, that's the background on why I'm involved here.
Thanks, guys. So before you chose your HDRM strategy, I guess what was your understanding of the whole test as you fly as you test requirement for your specific missions?
Yes, so this strategy highly resonates with us. So this is what we are living since the beginning. It starts with our model philosophy. So we test as much as we can with our flight model. What we cannot test with our flight model, therefore we have a completely identical engineering qualification model. For example, when you think about radiation tests, you do not want to radiate your flight model already before it goes into space. So we try to mimic everything as far as possible. As I said, we're doing laser communication, and one thing that is a good example for our test as you fly approach is when we test our optical track. We went to, so in the end-to-end test, we went to a parking place which is 3 kilometers away from our site. So we used the final optical ground station, we used the final terminal, in that case the EQM, that we have real atmosphere in between of our optical link, because we have a lot of tools to mimic all these conditions. We have fading test beds, we have simulations, but only the real environment gives you the real behavior. And this is always our approach. And also during testing and during qualification, we use the exact same ground station, we use the exact same cables. Everything must be completely identical to the final mission, because everything can have an influence on the outcome.
Yeah, and kind of the same approach, with us is essentially building these deployable antenna arrays. I did most of the development. We were a very small team. I'm doing was doing all the mechanical engineering and design on that. So I needed to be able to get parts very quickly, test them, determine if they were going to be suitable, and then essentially anything that wasn't off the shelf, I was just going to design my parts around, because I didn't have time to have too many things custom made by their vendors. So actually the selection of the HDRM came extremely early in the development process. We knew it would work in the bus. We okayed it with our bus vendor, and then essentially picked out where it was going to fit on their bus. And then I essentially designed the deployable around that. So we had an engineering unit here and at my house, and then I used kind of like the lab that I built here to prototype and test around that. So I did a lot of test deployments and essentially took it from the development kind of stage all the way through qualification testing, even to flight, without changing that aspect. So the other things sort of changed around it, or evolved around it, I should say. But yeah, so getting the parts in very early and developing with the actual, equivalent hardware was super important for us and vital to the success of the program. So it was design, prototype, and test as you fly in our case. So
very cool. So I'm going to switch the order here. And so on the second question, Dave, I'm going to come right back to you first.
Sure.
Especially on this size of satellite, we see, a lot of people traditionally have gone towards the burn wires or the pyros. What solidified your decision to go with resettable mechanisms versus one of those solutions?
I'm far from an expert in developing space hardware, but I never really liked this idea of this sort of of refurbishing parts and then having to take things apart and put a new piece in that's going to burn, like these consumable items. I know this has been kind of a standard in the industry for a long time, but it kind of seems like you're introducing an element of the unknown, a little bit of risk each time. Of course, every approach has risk, but I also knew that we were going to have to do a lot of different deployments of our little system during development and testing. We didn't really know. We were kind of developing this process as we went. It was pretty new for us still as a company, and again, being pretty much the one driving this and doing it myself, I needed something where I didn't have to worry about any kind of downtime, disassembling things, refurbishing parts. I wanted to have everything in one package where I can do it quickly, and thankfully that approach worked really well for us. I didn't want to limit testing or learning or anything based on having some refurbishable part or anything like that. So that was kind of core to the decision. I knew it was going to let us develop and test without any other roadblock, essentially.
Fantastic. Ben?
Yeah, it was kind of the same for us as well, but also, especially in the laser communication, there were also other great advantages we saw at the pin pullers at that end. So we used the pin pullers. We are building prototypes, so we're doing this for the first time, and you often do not know the outcome. You do not have a product which you build until the end. You go to qualification and everything works perfectly. This is not gonna happen, especially not in science. So we're building prototypes, we are doing multiple iterations, and you want to test everything, the whole chain. So you want to test the software, that the software releases it. You want to test the electronics, that the electronics of the release mechanism works. You want to test the mechanics, and you have to test this many times. And we considered burn wires very early in the beginning, and we directly saw that this is not usable at all. So then we went for research, and then we finally found then Dcubed, which was pretty easy for us to find, you guys. But that was one of the major points, this high repetition of tests, of qualification tests that you could achieve. And another aspect for this pin puller was when you compare it to pyros and burn wires, we have a relatively not that high load, but still of a burn wire. It did not really feel comfortable to have such a thin wire, even though the loads should have withstand it. But we are talking about very compact, very efficient designs. So everything is very close together. And everything that burns can lead to some point of contamination. And we are doing laser communication. So we have a surface flatness of our optical elements up to lambda over 14. So every tiny particle which sets down on our optics can have an influence on the signal. And even if the burn wires or the pyros, they do not contaminate much in a classical way, for optics, this can be crucial. And that was another aspect where we said, these pin pullers, they make sense. They have a compact design, which still fits into our system. And the system, it's mostly surrounded by optics. So you do not want to have anything contaminating this. And with this very compact design, that was the point why we then in the end choose the pin pullers, and the rest, Dave, you already explained it very well. The other aspects with high repetition and fast retesting if you need to.
Awesome. Thank you for that. Just a reminder, guys, if any questions come up as we're going through this, please feel free to drop them in the chat. So I'm going to bring again back to you, Ben, and we'll switch directions again. 2 parts here. You've kind of mentioned which units you're using, but if you could just clarify which Dcubed product you were using, and then just walk us through the verification campaign and how the HDRM kind of played into that process for you.
Yes. So for this webinar, I brought one of our laser terminals, and this is exactly the terminal where we used the pin puller. So a laser communication is very directed.
Wait, Ben, hold on one sec. Can we make Ben bigger so that he can show off?
Yeah, I've just done it.
Okay.
Go ahead, Ben.
Cool. All right.
Okay,
go ahead, Ben.
perfect. So laser communication, it's very directed, because the high data rates you can achieve only with this very narrow beams. With this, you increase, you can reach the high power density on ground. And to be independent from the satellite's attitude, we developed this, what you can see here, that's the coarse pointing assembly. This is basically a prism that acts like a mirror. And with this coarse pointing assembly, we can steer the beam in every direction. So we can describe the whole hemisphere and are completely independent from the satellite's attitude. But you can already see we have a very sensitive prism, as this prism is made of glass. It's an optical element. We have very precise mechanics. So we have very thin ball bearings for the CPA, and all of this has to withstand the loads of the launch. And that was the point where we used the pin pullers for. So we use pin pullers as launch locks. So we have 2. One comes which you can maybe you can see it through the prism reflected here. So there's a pin puller going into the side wall that blocks the elevation angle, and then down here you might not be able to see it. So it's inside, it's on the inside of this plane, which blocks the elevation axis. And these two pin pullers, it could not move, and in the end could also withstand the vibration loads. So this terminal is not in space yet, but we qualified it on the Athene-1 satellite. It's a project Bundeswehr. The mission is Grant. It's basically a flying lab. And even though this terminal is designed for kids, and the pin pullers with this compact design made it possible that we could fit into the CubeSat standard, the Athene-1 satellite, it's a small satellite which does not fit into a deployer. So the loads were higher than we expected in the beginning. And that was the point where we said we want to de-risk our qualification. We go on the shaker in advance before the qualification. We tested how can we achieve these loads, or how high can we go with our loads. And that's exactly then helpful with this pin pullers, that we could reset them again, that we could do multiple tests in advance before we then did the final qualification with the terminal and then also with the satellite.
Awesome.
Yeah,
Thanks for sharing the hardware.
For us, we had a similar scenario. I mean, we, like I said, we were kind of developing our qualification and proto-flight test strategy as we went. We did have, as I said, we were launching on a 16U CubeSat. So we had a bus vendor that was building essentially the CubeSat for us, and then we attached our deployable antenna to it. So kind of the way that we did we couldn't fully do like a test on a CubeSat chassis, like when we got to Vibe and everything. So what we did instead is essentially built a plate that simulated one side of the CubeSat. We had these, this is kind of the antenna array. It's actually two parts. I don't have the hinges on here, but it deploys outward like to be about this big. And there was 4 of these arrays on each, so one on each side of the satellite. So we used 4 of the release nuts on each satellite, one for each of these branches. So in the test campaign, essentially, we simulated the full hardware on one side and one side of the spacecraft, and then we shipped them to the bus vendor. That way, they could unbolt it all. But so when we got to, doing our environmental testing, we had all the flight hardware, mounted on this one bracket that simulated the spacecraft bus, but also had all the holes and everything for like the Vibe shaker tables and everything. So what we were able to do is essentially assemble each deployable on a panel that exactly matches the flight bus interface. So we did a lot of deployments during that verification and like flight acceptance, or you want to call it proto-flight testing. So as soon as I had it assembled, I could fire the HDR on, make sure it deploys cleanly. And then we packed them up, took them to go through Vibe and thermal vacuum. And essentially, since the setup is like so simple and everything is reusable, I just brought a battery pack with me that would let me, after each vibration axis, I checked. We did proto-flight testing on every branch, every one of these that we flew, so every single article, because we wanted to be very sure that they're going to work. So we had 2 satellites, so we had 8 of these deployables, and then we had a couple spares as well. So say 10 units. And so at the test facility, I had these all going on and off the vibe tables. And so the advantage to having the release nut on there was that after each vibe axis, I could test fire every unit and make sure, one, that the HDRM was still working, two, that nothing else in the mechanisms, you know, was jamming. Basically, that the whole deployable was still functioning as it should. And, you know, time at these facilities is expensive. You want to get in and out of there normally pretty quickly, and you just don't want to delay things. So, and also we didn't really have any personnel. I was the only person from the company there doing, you know, as the responsible engineer at the test facility. So it enabled me basically to do all the hardware checks myself. Just being able to hook up this battery pack, fire HDRM, reset it, go to the next one, and then go through them, and then, you know, essentially unbolt everything from the table, reorient it for the next axis, and go on. You know, so at basically any point, we were able to verify that the deployables were working, that the HDRMs were working, and then be confident that we could go on to like the next phase and not have any real uncertainties.
Awesome. Thanks for the detailed explanation. All right, I got one last rapid fire off the top of your guys' head. If you could have one improvement to make life a little easier on the HDRM, what would it be?
I've thought about this. I don't have like a major suggestion. I don't know, a little longer wire harness that comes with it, maybe. I don't know. Like they come with they came with a pretty short pigtail. I don't know, maybe something longer.
That we can do. That's easy peasy.
All right, Ben?
Yeah, there was one suggestion we already did to Dcubed, but as I learned in a later version, that was already solved, because we had the problem that it was hard to set when the terminal is integrated, because it has to be set with a tool from the back through the bottom of this payload. And unfortunately, when the payload is integrated, this is not accessible anymore. So we wanted to have something that you can set the pin puller again from two sides. And what I learned in the meantime, that you have a refurbished version with a thread in the pin that you can access it from the other side as well and set it again. So that was, yes, there was a request for improvement, but fortunately it was already solved. Maybe not for ours, as we already procured them, we already had them, but we know for the future.
Awesome. All right, thanks guys. Gonna hand it back to Valentina here, but really appreciate all of you guys' input and learnings and being willing to share.
Thanks, Kyle, and thanks also Ben and Dave for even showing the hardware with the direct application. That was really cool. All right, so we are actually getting closer to the Q&A time. So please don't be shy and keep your questions on coming, everyone. I'll now give it back to Guillaume, who's gonna. Teams allows me to change slide, all right, who will guide you through more examples on how customers use the Dcubed actuators and status as it applies it as compliant, lessons learned from integration, and it will also tell you why SMA actuators enable safer repeated deployment testing. Over to you.
Yep. So there's two different kind of approaches that we've seen in the past, and there's a lot of customers that they are thinking, oh, release NATs. Release NAT, we are going to load, and we are going to have a deployable, we are going to hold it, and it's going to be purely perfect, like this setup over here. We have something, and it will deploy perfectly straight. And there's no loads coming from nowhere else. But this is a perfect scenario. This is according to physics and so on. That's perfect. But in engineering world, there's always some engineer that decides that, let's drill a hole over here for lighting in this structure. And then the structure is not balanced, the center of gravity is shifting, and we are going into a different scenario. And that other scenario, as shown in the next slide, it's kind of slightly different. Maybe it's just a tiny difference on where the center of gravity is, or maybe it's huge by design, who knows. But the thing is that in those scenarios, any kind of dynamic loading applied, or not even dynamic loading, it can be also static loading. Loadings on those scenarios, they are induced in a moment into the mechanism. And a moment into the mechanism means that you have a lever arm and the preload requirements are increased over there. And therefore, sometimes people is not thinking about them. They are just thinking about the mass load that's giving me a force that I need to hold. We will compensate it with the preload. But the set, it depends also on where is the center of gravity of this mass and which is also the loading conditions, because dynamic loading can be kind of nasty and it's not always showing because it's kind of random. I mean, random excitation is random. There's a given probability that you will have some spikes beyond that random profile. So have in mind, have a safety margin and make sure that you're accounting and that you have enough margin on your actuator or on the preload that you're applying to cover all those kind of scenarios, especially because we've seen it many times with many companies. They are picking the HDRM at the beginning of a design, at the beginning of a project. They have in mind an architecture and suddenly the design is evolving, it's maturing. They already have the HDRM, but then the loading scenarios, they are different. So it's always a good idea to have something that, you know, it can take a bit more than needed. That's always a good approach. And that will be a big lesson learned. And also speak with us as soon as possible, because we are giving with the actuators, we are giving some engineering hours as consultancy hours, and we can discuss loading scenarios, we can discuss designs themselves, we can make design reviews. And this is something that is really, really handy, especially because those scenarios is something real that is happening in many companies, is something that sometimes it cannot be foreseen because the design is evolving and the people doing the HDRM is not the same people doing the deployable thing or the people doing the analysis. So it's team. And during the project, at some point, there's something that is working on a given stage. And because of a minor modification on a later stage, trying to fix something, you will need to iterate, or otherwise there's a chance that you will go into a test campaign and suddenly things will start happening. In any case, it's doable, and that's the beautiful thing of those actuators. They are so easy to reset that you are not just relying on one final test. You can actually test it multiple times along the life of the actuator. You can test it, as Dave was saying, you can test it during runs on a vibration test. Maybe it's not needed, but you can do it. And having this capability, it's super handy. And then we have, on the other hand, we have the pin pullers. On the pin pullers, the scenario is slightly different because of the loading configurations. Sorry, I forgot that on the previous slide, it was just like, if you have those kind of elements that are like offsetting and introducing moments, there's always ways of managing the thing. Like if you have hinges that are taking the moment, then you know that the hinge is taking the moment, not the HDRM. Or you can put a couple of HDRMs so that this thing is not actually wobbling around during dynamic excitation. And now, yes, for the pin pullers. On the pin pullers, there's a lot of customers that when designing that thing, they are thinking, yeah, the pin puller is not going to have any load on it because it's going to be in space. I just need to retract it and that's it. And the dynamic loading, it's over there. And it's over there because of the same thing. You can have a gimbal. If there's any misbalance, all the load is going to go directly into the pin puller that it's locking the motion of the device. And I'm pretty sure that, for instance, on that side, Ben, you have a lot of insights and a lot of thoughts about it, because it's something that is happening to pretty much everyone. You are designing something on the cat, it's looking perfect, you have a perfect balance on cat, and suddenly you add the harness in, and then you have additional weight, or you are modifying a given screw that it's longer or shorter or whatever. Having a perfect balance in real life is never existing, and therefore the loading conditions are going to be harsh on the pin pullers. Even if the retraction is going to happen at no load, during dynamic loading, as you can see on that picture, it can happen. And this was actually from a customer that was experiencing no load during vibrations. And then on the pin itself, what you can see over there, it's aluminum that it's welded directly into the stainless steel. And this was a no load condition for a pin puller. So you can imagine that
vibration testing, not only vibration testing, any kind of mechanical testing into those devices, it's critical because most of the loading conditions that during simulation and during analysis can be neglected or can be like assumed to be near zero or whatever. In real life, they can behave really differently. So it's really important as soon as possible, try to hit the test. In my personal experience, especially when rapid iteration is needed and when there's a lot of modifications on the payload, when the team is agile, the sooner they are hitting the testing phase, the better. And the better the access to test facilities, the more knowledge that they can gather. And yeah, finally, that's a thought that we have, because a lot of times we are getting questions about how reliable are our actuators, and they want us to provide a number. And in reality, reliability is not just about the actuator, it's about how the entire thing is being integrated. Not only the actuator, how is the process, whether if, like, how many actuations this actuator have seen, which were the loading conditions. There's a lot of things over there. Also, like, is it mounted using like screws that are torqued to specs, or the screws are loose, or there's many things, many things. So reliability should not be treated as a number. And that's something that is beautiful from this approach that the SpaceX is following is do not rely on numbers, rely on data. And data means if you have a test report, if you have something that has been tested and it's working, then it's working. If you're starting to modify things around, it's a different thing. So maybe you need to test it again. And with those actuators that we are providing, the beautiful thing is that if you need to modify anything else, you can still use the same actuator. And that's speaking for reliability. As far as the actuator is working, you know that this one is working. You don't need to get another one. You don't need to rely on a number. You are relying on data, on something that works. And that's the last thought that I had about reliability. Thanks, Valentina.
Thank you, Guillem. So we are almost at time, but the fun part now starts. Q&A, and you have the opportunity again to win this very springy Dcubed hat. There's one question right now in the chat, Guillem. I'll hand it over to you on that one to reply, and people keep asking questions as we go. So Forrest is asking, how many test and reset cycles can Dcubed HDRMs do? What's the expected failure mode when exceeding that number?
All right, so most of our actuators, they can do more than 100 actuations, most of them. And I'm saying more than 100 because normally when we are hitting the 100 actuations out of an actuator, we stop testing this actuator. We don't want our technicians to suicide. So it's a, it's a number that we are giving, but we know that it's better. The actual failure mode that may happen afterwards, there's different things. So for instance, we have the SMA element itself. The SMA element is dimensioned by design so that it can take millions of cycles. So it will never be the failure mode or the blocking point unless it's overheated. If it's overheated, then the SMA will anneal, and that can lead to some other issues of non-actuating and so on. But that's a mistreatment, and that's something that is indicated on the user manuals on how to use it. If this is followed, the immediate failure mode that may happen, it's the wear down of the mechanical parts. So we have a set of coatings, we have some solid lubrication coatings over there, and some elements that can wear down. And those elements, in principle, they are dimensioned to wear down on the range of hundreds of thousands of cycles. But also it depends on the loading conditions. Some of them, they may suffer a bit more because of whatever the reason, the loading conditions or something like that. But in principle, they should take a lot of cycles. And yeah, as I said, more than 100. And some other actuators, for instance, the milli actuator, I was mentioning that it depends on the load. And that's obviously because of the same, like on those load levels, the wear down is quite significant on all the treatments that we have on the metal parts as well as on the coatings. And over there, what it's limiting, it's 15 kilonewtons. That, of course, it's making an impact, a huge impact on the wear down. And therefore, it cannot take more than 80 actuations, or it can take a bit more than 80 actuations at 10 kilonewtons. But we always like to keep some margins on our side. But well, that will be the immediate failure mode.
Thanks, Guillaume, and thanks again, Forrest, for the question. We have another one from Indra saying, is the pin puller or DHRM suitable for operations in the lunar surface, especially in terms of tackling the lunar dust? So as Dcubed in general, we have several projects actually going on to the moon, both on the HDRM and the solar array side. So of course, depending on how you use it, where you use it for the applications, yes, it is suitable. As HDRM, happy to receive your say more information on what you're planning to do and see how we could potentially support you if that's your of your interest.
Maybe
Then
I would like.
from Carl, I'll go ahead just because we're almost at time yet. Sorry.
Right.
I'll go on, Carl, and probably hand it over to you. Will the voltage actuation from the new 15 kilonewton nut be carried over to the smaller actuation in the future, or will they stay current driven? And please keep the answer short here. Thanks.
It will stay current driven. Mainly the difference is that on the inside of the smaller ones, we have a short piece of SMA on the range of 100 millimeters. We are not going to say the number, but on that range. On the big ones, we have. What, sorry?
Go ahead.
On the big one, we have meters, a lot of meters, and therefore the resistor value of the SMA is changing a lot, and it's allowing us to use such a high voltage source. That's the main difference, and it's something that it will not go retroactively to the nanos or the micros.
Perfect. Then I'll take one last from Shiva. Since the SMAs are triggered via heat, is there any concerns that a large thermal gradient across the device can cause an issue with its proper deployment? How should we test for it, and have you tested for it? So yes, of course, that is, if you want to call it like that, a failure mode of the actuators that we have, SMA based. Considering the SMA capability and temperature range, you then need to work with that. We have customers that use it, for example, in drug sales. So they have tested and sort of isolated the mechanisms well enough so that they can survive the 5 years in space, for example, or that they are using it in a re-entry vehicle. So there is a limitation. If you download a data sheet or even just go on our website, you will see that the temperature range given is minus 65 plus 75, but there are ways to go even above that, and it always depends where you're putting the mechanisms and for how long it is staying at that temperature over the 75, sorry. Perfect. I would say we are at time. So thank you everyone again for the best question. We'll contact the people privately and award a few of you guys. Thanks again to Ben and Dave for staying with us today and sharing your more about your projects, what you're doing at DLR and Hubble, and how our actuators have been useful for you so far. In case there's additional questions for us, for Dcubed, feel free to drop an email to sales@DCUBEDspace.com. We'll be happy to answer any additional technical, commercial questions or any type. And yeah, with this, I conclude the meeting. Thank you again, everyone, and see you to the next Dcubed webinar for our conferences.